Something just happened in deep space. A signal started pulsing through the dark, again and again, slow, steady, almost like a heartbeat. Scientists were not expecting this. Nobody was. Because whatever sent it was not acting like a normal star, not like a normal dead star, and not like anything we thought we understood. And here's the part that makes this bigger than a strange astronomy headline. If this signal really is what it seems to be, then what you're about to hear could change how we understand the most extreme objects in the universe. Far beyond Earth, beyond the moon, beyond the planets, and far outside the world you know from the night sky, the universe is always sending out signals. Most of them are messy, some are weak, some are so common that astronomers can sort them into old familiar groups. A pulsar spins and flashes, a black hole feeds and glows. A star explodes and leaves behind a remnant that slowly fades into the dark. Over time, scientists learn the patterns. They learn what kind of object makes what kind of light, how often it blinks, how strong it should be, and what story the data is trying to tell. That is how modern astronomy works. It is less like looking through a telescope and more like listening to a huge cosmic orchestra where every instrument plays its own rhythm. But every now and then, one sound appears that does not belong in the music. One beat lands where no beat should be. One pulse refuses to fit the rules. And that is exactly what happened here. The object at the center of this mystery has a name only astronomers could love. ASCAP J8832-0911. Not a dramatic name. Not the kind of name that tells you what it is. Just a coded label based on where it sits in the sky. But behind that cold name is something deeply strange. This object lies around 15,000 light years away from Earth inside our own Milky Way galaxy. That distance is almost impossible to picture. The light reaching us from it tonight began its journey long before. Human history looked anything like it does now. Long before cities, long before machines, long before anyone on Earth knew what a galaxy was. And yet, after all that time, the signal arrived here and landed in the hands of people ready to notice that something was wrong. The first clues came from radio astronomy. That is the branch of science where telescopes do not just collect visible light. They listen for radio waves, a kind of light your eyes cannot see. This matters because some of the most violent and exotic objects in the universe are easier to find in radio than in ordinary light. In Western Australia, on Voyager Yamaji country, there's a powerful instrument called the Australian Square Kilometre Array Pathfinder, or ASCAP. It scans huge sections of sky at once, which makes it good at catching things that flare up without warning. In late 2023 and early 2024, ASCAP picked up bright bursts from this object. Not tiny flickers, not random static. Clear, repeating pulses. Each one lasted about 2 minutes, and the full cycle repeated every 44 minutes. That may not sound shocking at first. A pulse every 44 minutes? So what? But in astronomy, timing is everything. Pulsars, which are spinning neutron stars, can flash many times every second. They are incredibly fast. Their whole identity is built on speed and regularity. This object was doing something thousands of times slower. It was not ticking like a cosmic clock. It was thumping. Slow enough that you could almost feel the pause between each burst. Slow enough to sound less like a machine gun and more like a heartbeat in a silent room. And that slow rhythm put it into a rare and puzzling category called long-period transients. Long-period transients are one of the newest mysteries in astronomy. Scientists only started identifying them in recent years. They are objects that give off bright radio flashes every few minutes or every few hours, much slower than a normal pulsar. Fewer than a dozen were known when this discovery began drawing attention. That alone would make them interesting. But what really keeps astronomers awake is that nobody fully agrees on what they are. Some might be magnetars, which are dead stars with magnetic fields so intense they can distort matter and release enormous energy. Some might involve white dwarfs, the dense burned-out cores left behind when smaller stars die. Some might come from binary systems where two stars orbit so closely that their magnetic fields collide. Each idea explains part of the puzzle. None explains everything. And then this new object made the puzzle worse. Because what scientists found next was not just more radio pulses, it was something much harder to explain. By what seemed like a lucky accident, NASA's Chandra X-ray Observatory was looking at the same patch of sky at the right time. Chandra was not hunting this object. It was aimed at something else. But space does not care about our plans. Sometimes the biggest discoveries happen when the universe interrupts the schedule. While ASCAP was catching the radio pulses from ASCAP J1832, Chandra picked up X-rays from the very same source, not once, repeatedly. The X-rays rose and fell on the exact same 44-minute cycle. That changed everything. Radio waves are one thing, X-rays are another. X-rays usually come from places where the universe is at its hottest, most violent, and most energetic. They often mean something extreme is happening, matter crashing onto a dead star, gas being heated to millions of degrees, magnetic forces snapping and releasing stored energy in a blast. To find radio and X-ray pulses together, matched like steps in the same dance, told scientists this was not just a weird radio source. Something dramatic was taking place around or inside this object, something powerful enough to shake multiple parts of the electromagnetic spectrum at once. But here is where things take a strange turn. The more data researchers gathered, the less this object behaved like anything they knew. The pulses were not only synchronized in radio and X-rays, the source also changed brightness by huge amounts over time. In some observations, it was blazing with unusual strength. In later observations, months afterward, the X-rays had faded away. That meant this thing was not just pulsing, it was changing states. Almost like it woke up, pounded a message into the dark, and then slipped back into silence. Imagine hearing a heartbeat through a wall, strong and steady, and then coming back later to find the room quiet. Was the source gone? Was it sleeping? Was it changing form? That uncertainty is where the fear and wonder begin to mix. One of the scientists involved described the X-ray detection as like finding a needle in a haystack. That was not an exaggeration. ASCAP can watch a huge field of sky. Chandra sees only a small piece of it at a time. The chance that both would catch the same strange object during an active phase was remarkably lucky. And luck matters in astronomy more than people think. We like to imagine science as perfect planning and neat results, but often it is patience, timing, and the rare moment when the universe decides to reveal itself. If Chandra had looked somewhere else that day, this might still be only a radio mystery. Instead, it became something much larger. To understand why this is so important, you have to step into the shoes of the scientists. When a signal comes in, the first goal is not to chase the most exciting idea. The first goal is to kill the excitement, rule out errors, rule out local interference, rule out broken instruments, stray satellites, weird processing effects, and human mistakes. Astronomers are trained to be skeptical because the universe is hard enough without fooling yourself. So the team checked the timing. They checked the location. They compared data from different instruments. They looked at how the pulses lined up. And what kept coming back was the same answer. The source was real. The radio pulses were real. The X-rays were real. That is when the real mystery began. Could it be a pulsar? At first glance, that sounds tempting. Pulsars pulse. That is literally what they do. They are the crushed cores of massive stars, city-sized neutron stars spinning at incredible speed. As they rotate, beams of radiation sweep through space like lighthouse beams. If one points toward Earth, we see a pulse every time it swings past us. But ASCAP J1832 is far too slow for a normal pulsar. A 44-minute cycle is wildly outside the usual range. Even stranger, the radio brightness and X-ray behavior do not fit what astronomers expect from standard pulsars. You can push the theory, stretch it, try the edges of possibility, but it still does not sit right. Could it be a magnetar? No, that is more interesting. Magnetars are neutron stars too, but they are the monsters of the family. Their magnetic fields are among the strongest known in the universe. They can crack their own crusts. They can release giant bursts of X-rays and gamma rays. If any kind of dead star might produce something extreme enough to match this signal, a magnetar is a serious candidate. In fact, some features of ASCAP J1832 could be explained by an old magnetar, one perhaps more than 500,000 years old, with an unusually strong magnetic field still active in its crust. That idea helps explain how such a compact object could produce energetic emission, but it creates new problems too. An old magnetar should not be this bright and variable in radio, at least not under the usual models. So magnetar is possible, but not comfortable. And then comes the white dwarf idea. A white dwarf is what remains after a star like our sun runs out of fuel. It does not explode in the same way massive stars do. Instead, it sheds its outer layers and leaves behind a dense hot core, roughly the size of Earth, but with a large fraction of a star's mass packed inside. White dwarfs are common. We know a lot about them. But under the right conditions, especially if paired with another star, they can behave in surprising ways. Earlier work in this field showed that at least some long-period radio transients may come from white dwarf systems, where a white dwarf and a small companion interact through their magnetic fields. In one study, a white dwarf and a red dwarf orbiting each other every couple of hours produced radio pulses in a way that looked bizarre until the system was finally identified. That discovery gave astronomers hope that maybe these heartbeat-like signals were not new physics after all. Maybe they were just a rare kind of stellar relationship. Then ASCAP J1832 showed up and ruined the easy answer. Because if this object is a white dwarf system, it would need to be extreme even by extreme standards. One interpretation is that it could involve a white dwarf with a companion star and an unbelievably strong magnetic field, perhaps stronger than any known white dwarf field in our galaxy. That is not impossible. The universe has a habit of embarrassing our sense of what is likely. But if that is the explanation, then this is no ordinary white dwarf. It would be a record breaker, a system sitting at the very edge of what our models can handle. And once you start living at the edge of the models, you have to admit something uncomfortable. Maybe the models are incomplete, but wait, it gets stranger. On the sky, this object appears close to a supernova remnant, the ghostly remains of an exploded star. At first, that seems important. If the source sits inside such a remnant, maybe it really is a neutron star born in the same explosion. That would support the magnetar, or exotic neutron star idea. It is exactly the kind of clue scientists want. But after studying the data, the researchers concluded that the alignment is probably just a line of sight coincidence. In other words, the object may only look like it is inside the remnant from our point of view. It may not actually be connected at all. That one detail matters because it removes a neat story, just when everyone wanted one. Instead of narrowing the mystery, the evidence pushed the door open again. This is the part many people miss when they hear space news. The discovery is not just the signal itself. The discovery is the failure of old categories. Scientists live by classification. Put an object in the right box and the rest of the reasoning begins to flow. How old is it? How massive is it? What powers it? What should it do next? But every so often, nature hands us something that refuses the box. Not because the data are bad, but because reality is wider than the map. ASCAP J1832 seems to be one of those objects. It sits between explanations. It borrows features from more than one class. It behaves enough like known things to tempt you, but not enough to let you relax. And here is where the story becomes more than a technical mystery. When you hear the phrase, heartbeat from deep space, your mind does something very human. It connects rhythm with life. It hears repetition and imagines intention. Of course, scientists are not saying they found a giant heart beating in the galaxy. They are describing a pattern, a pulse, a regular rise, and fall in energy. But the emotional effect is real. There is something eerie about a signal that arrives in steady intervals from the dark between stars. It touches an old part of the mind, the part that listens for meaning and sound. A drip in a cave, footsteps in an empty house, a heartbeat in the silence. Even when you know the explanation is astrophysical, the feeling remains. Because rhythm is intimate. Rhythm feels alive. That emotional reaction matters more than we admit. Space stories that stay with people are not only about numbers. They are about contact with the unknown. They are about the moment where hard data meets human imagination. And ASCAP J1832 sits right in that space. It is not just far away. It is hard to categorize. It is not just energetic. It is timed. It is not just strange. It is strange in a way that sounds familiar to us, almost biological, even though it comes from something almost certainly dead, collapsed, burned out, or broken by forces beyond daily understanding. The contrast is part of what makes this discovery feel so haunting. But let us slow down for a second and look at what the researchers actually saw. The radio pulses lasted around 2 minutes. Then the source went quiet again until the next cycle. 44 minutes later, another bright pulse. In the X-ray data, the source rose and fell on the same schedule. This repeating behavior was not a one-off blip. It was coherent, structured, measurable. In its bright phase, the object became one of the strongest radio sources of its kind ever recorded, with radio brightness so intense that only a tiny number of known objects in the sky have reached similar levels. That alone is wild, but matched with periodic X-rays, it becomes almost absurdly rare. The researchers described it as the first long-period radio transient ever seen to emit X-rays in this way. In other words, this was not just another example of a known class. It was the discovery that expanded the class itself. And then, 6 months later, Chandra looked again and found no X-rays from the source. That detail can sound small, but it is crucial. It tells us the object is transient in a deeper sense. It has active phases and quiet phases. Maybe it only produces X-rays under certain conditions. Maybe the geometry changed. Maybe matter fell onto it for a while and then stopped. Maybe the magnetic field twisted, released energy, and relaxed. Or maybe we are seeing a system with cycles inside cycles, a larger pattern not yet mapped. The truth is that astronomers do not know. And if that makes you uncomfortable, good. That means you are feeling the real texture of science. Discovery is often not a clean answer. It is the arrival of better questions. Here is the strange turn again. The more exciting the observation becomes, the more careful scientists must be. There is always pressure from media, from the public, even from the thrill of discovery itself, to turn every mystery into a story with a neat ending. People want a label. They want the alien answer, or the black hole answer, or the dramatic one-line explanation they can hold in their head. But the experts closest to this discovery are doing something far more interesting. They are resisting the easy label. They are saying, yes, this is astonishing. Yes, it may point toward a new type of physics or a new pathway in stellar evolution. But no, we do not yet know what object is producing this heartbeat-like signal. That kind of honesty is not a weakness. It is the strongest sign that the mystery is real. So what did the experts think when the data came in? According to reports around the discovery, the reaction was a mix of excitement and disbelief. Researchers involved in the project described the find as unlike anything they had seen before. Others in the field, including scientists who had studied related long-period transients, called it exciting because it seemed to bridge a gap between the most extreme magnetars and the weirdest white dwarf systems. That phrase matters. Bridge a gap. It suggests this object might not belong fully to one old category or another. It might sit in the middle or show us that categories we thought were separate are actually connected by hidden states of matter and energy we have barely begun to understand. That possibility is huge. Because if ASCAP J1832 is a magnetar behaving in a way we did not predict, then our models of how magnetars age, store magnetic energy, and emit radio waves may need revision. If it is a white dwarf system with a magnetic field stronger than any known example, then we have found a type of stellar engine more powerful than expected. If it is neither, then astronomy has just opened the door to a new class of compact object or a new emission mechanism altogether. Any one of those outcomes would matter, not because it changes your morning commute or the weather next week, but because it changes the map of what the universe allows. And humans live by maps. For most of history, the sky looked fixed. Beautiful, yes, but distant and unchanging. Then telescopes arrived and we saw motion. Then spectroscopy revealed chemistry. Then radio astronomy revealed invisible storms. Then X-ray observatories showed us hot, violent processes hidden behind ordinary starlight. Every time we added a new way of seeing, the universe became less calm and more alive. Not alive like an organism, but alive with events, eruptions, collisions, pulses, and transformations. The old silent sky turned out to be noisy beyond belief. And discoveries like this one remind us that even after centuries of study, there are still beats in that noise we do not recognize. This is also a story about teamwork across the planet. ASCAP in Australia helped spot the radio activity. Chandra in space caught the X-rays. Other instruments and collaborators from multiple countries helped verify the behavior and narrow the location. Newer systems built to catch mysterious signals, including tools designed to sift huge amounts of sky data quickly, played a role too. That matters because the sky is too large and too active for any one telescope to solve alone. Modern astronomy is becoming more like a global nervous system. One instrument notices a twitch, another zooms in, and both were rising and falling together every 44 minutes.